three-phase synchronous generators. In this video, we are going to discuss about relationship between electrical angle and mechanical angle, frequency of generated voltage, synchronous speed of synchronous generator, winding terminology, different types of windings, and EMF equation of synchronous generator. Coming to the relation between electrical angle and mechanical angle in three-phase synchronous generator. So we know that one rotation is equal to 360 degrees mechanical angle. When we see the waveform, one sinusoidal wave, that is one cycle is equal to one positive cycle of induced EMF plus one negative cycle of induced EMF. So this completely, two cycles will constitute 360 degrees. So in the waveform, whichever angle is shown is known as electrical angle. Let us consider a two-pole alternator. In a two-pole alternator, one mechanical angle corresponds to one electrical angle. So if the rotor rotates 360 degrees, that is completes one cycle mechanically, it is not equal to one complete cycle of a sinusoidal wave. So therefore, for a two-pole alternator, one mechanical angle is equal to one electrical angle. But in general, the relation between the mechanical angle and electrical angle is one mechanical angle is equal to P by 2 electrical angle, where P is equal to number of poles, F is the frequency of induced EMF, and N is the speed of the rotor. So this is how the relation between electrical angle and mechanical angle is. For example, if we take a four-pole alternator, for a four-pole alternator, one mechanical angle, that is 360 degrees, is equal to two electrical angles. So for one rotation of your rotor, you will get two sinusoidal wave cycles or generator. Similarly, for a six-pole alternator, three sinusoidal cycles or generator. So in this way, mechanical angle is related to the electrical angle as one mechanical angle is equal to P by 2 electrical angle. Now coming to the frequency of generated EMF. So just now we have brought the relation that one mechanical revolution is equal to P by 2 electrical cycles. So therefore, how many electrical cycles will be there per revolution? It is equal to P by 2, where P is the number of poles. We know that the speed of synchronous generator is represented as N RPM. In 1 second, the rotor will complete N by 60 revolutions. Therefore, frequency, which is defined as number of electrical cycles per second, can be written as number of electrical cycles per revolutions into revolutions per second. We know that number of electrical cycles per revolution is P by 2 into revolutions per second is written as N by 60. So that is equal to Pn by 120. So therefore, frequency can be expressed as Pn by 120 Hertz. This is the expression for frequency of a generated EMF, where P is the number of poles, N is the speed in RPM, and F is the frequency of generated EMF, which is represented in Hertz. Now let us find out what is meant by a synchronous speed. The speed at which the three-phase synchronous generator rotates is known as synchronous speed. And usually the synchronous speed is denoted by N suffix S. So it is given by the expression where S is equal to 120 F by P. So usually this expression has come from the previous expression. So we have represented frequency is equal to Pn by 120. So here the speed, whatever we are representing, we can consider it as a synchronous speed in case of three-phase synchronous generator. So from that expression, we can write Ns is equal to 120 F by P. So this is the expression for synchronous speed of three-phase synchronous generator, where F is a rated frequency in Hertz and P is the number of poles. So in India, the frequency of an alternating EMF standard value is 50 Hertz. Now let us discuss about some winding terminology before going to derive the EMF equation of three-phase synchronous generator. So the first terminology is conductor. What is meant by a conductor? So it is a part of a wire which is under the influence of a magnetic field and it is responsible of EMF induced in it, which is known as a conductor. So that means it is the active length of a wire in which EMF is induced is called conductor. So usually these conductors are placed in the slots. You can see here. So this portion in the figure represents a conductor. Next definition is turn. What is meant by a turn? You can see in the figure here, figure a conductor which is placed in one slot is connected to the conductor which is placed in another slot. These two conductors which are connected together present in two different slots is constitute a turn. Okay, so that means we can say that two conductors constitute a turn. Next, coil. As there are number of turns present in a slot, you can see the figure B. See here, this represents a coil side. So a coil side is present in one slot. So in this coil side, there will be number of conductors present. So the conductors which are present in one coil side are connected to the conductors which are present in the another coil side. This total combination, this total setup is known as coil. So coil is nothing but when a the coil side present in one slot is connected to the coil side present in another slot, then it constitutes a coil. A coil may consist of number of turns. It may consist a single turn, which is known as a single turn coil, or if it contains more than one turn, we call it as a multi-turn coil, which is shown in the figure here. Next, coil size. As I told you, coil consists of many turns. So the number of turns, all these coil size, these turns are wrapped together, and the portion which is present in a slot is known as a coil side. Coil span. Coil span is nothing but the peripheral distance between the two sides of a coil. You can see the figure here. So there is one coil side present under north pole and another coil side present under south pole. So these coil sides are connected together. The coil side present under north pole is connected to the coil side present under south pole. So the distance between the two coil sides is known as coil span. Usually this coil span is measured in terms of number of armature slots. If we see the figure here, so totally it is marked, it is numbered. The number of coil slots present between these two coil sides are 3. Therefore, the coil span in this example is 3 armature slots. Next, coming to the definition, pole pitch. The pole pitch is defined as the peripheral distance between the center of two adjacent poles in a DC machine. You can see the figure here. So there is a north pole here and there is a south pole here. So the distance between the center of these two adjacent poles is known as pole pitch. Even the pole pitch is also measured in terms of number of armature slots or number of armature conductors placed between two adjacent poles. Therefore, we can calculate the pole pitch as pole pitch is equal to number of slots per pole. Also, we can say that one pole pitch is equal to 180 degrees electrical. So this is about the winding terminology. Now coming to the different types of windings in the three-phase synchronous generator. There are different types of windings used in three-phase synchronous generator or alternator. So these windings can be classified as single layer and double layer winding, concentrated winding and distributor winding, full pitch coil winding and fractional pitched coil winding. Now let us discuss about the single layer and double layer winding. You can see here the figure. Single layer winding. If there is only one coil side present in a armature slot, then such type of winding is known as a single layer winding. And you can see the next figure. If there are two coil sides present in a armature slots, so one coil side is present in the upper layer and the other coil side is present in the lower layer. So this type of winding is known as double layer winding. Usually for our alternator, we prefer double layer winding as we can accommodate more number of conductors so that the more EMF is induced. Next, concentrated winding and distributor winding. What is meant by a concentrated winding? If the conductors present in a coil side are all connected together, then such type of winding is known as a concentrated winding. Whereas the conductors present in one coil side under one pole are connected to the conductors present in the another coil side which are present in the some other different pole, then such type of winding is known as distributed winding. So the type of winding that is used in alternators is usually the distributed winding. The distributed winding has many advantages when compared to that of concentrated winding, as the harmonics will be reduced and the EMF induced will be more sinusoidal in nature. So hence distributed winding is preferred in case of three-phase alternators. Now coming to the full pitched and short pitched winding. So what is meant by full pitched winding and short pitched winding? If the distance between the two coil sides is equal to a pole pitch, otherwise we can also say like this: if the coil span is equal to pole pitch, then the type of winding is known as full pitched winding. So in full pitched winding, the EMF induced in the conductor is the arithmetic sum of all the EMFs induced in the individual conductors. Okay. What about the short pitched winding? If the coil span is less than the pole pitch, then the type of winding is known as a short pitched winding. Or we can say that the distance between the two coil sides is less than a pole pitch or less than 180 degrees electrical, then the type of winding is known as short pitched winding. The short pitched winding has more advantages than that of full pitched winding. So by using the short pitched winding, we can save the amount of copper material. Also the EMF induced in the conductors will be of more sinusoidal in nature. That means the number of harmonics present in the EMF induced wave is minimum and compared to that of full pitched winding. Hence for three-phase alternators, the short pitched winding is preferred. So when we are discussing about these types of winding, for our three-phase alternators, the most preferred type of armature winding is double layer, distributed and short pitched winding. And also in a three-phase connections, we have two types of connections. One is star connection and delta connection. Usually we prefer star connection for three-phase alternators when compared to delta connection. Therefore, finally we can say that for three-phase alternators, we consider a star connected, double layer, distributed and short pitched winding. So this is about the different types of winding. Now let us discuss the important part, that is derivation of EMF equation of an alternator. So to derive the EMF equation of an alternator, so we have to define some number of terms. Let us see here. Let us consider Z as the total number of conductors. So we will represent the total number of conductors by using the letter Z. Because we are discussing about three-phase synchronous generator, then the number of conductors per phase is represented as Z per phase. Next, T phase, number of turns per phase. We know that two conductors constitute a turn. So if there are Z phase number of conductors, then the number of turns per phase will be Z phase by 2. Therefore, T phase is equal to Z phase by 2. And as usually we know that Ns is equal to synchronous speed in RPM, whose expression is given by 120 F by P, where F is the frequency of induced EMF, P is the number of poles. And let E phase be the phase voltage, that is EMF induced in each phase in volts, and phi will be the flux per pole in Webers, and EL is equal to line voltage. Because we are considering a three-phase synchronous generator, so we will be discussing about both phase voltage and line voltages. So when we are doing the derivation of this EMF equation, we are going to find out first the expression for EMF induced in each phase, that is E phase. Now considering after that, we will consider whether the alternator is a star connected or delta connected, then we will find out what is the value of its line voltage. Now let us start the derivation. We know that the EMF is induced in the armature winding as per the Faraday's laws of electromagnetic induction. So from this we know that the average value of EMF induced in a conductor, in a single conductor, is given by the expression d phi by dt, which is nothing but rate of change of flux linkages. Rate of change of flux linkages is given by the expression d phi by dt. Now We know that the flux cut per conductor per revolution, which is nothing but d phi, is given by phi into P. So because we have defined phi is the flux per pole, and how many number of poles will be there? There will be P number of poles. So what is the total flux by the conductor in one revolution? It is given as P into phi. So therefore we know that d phi is equal to P into phi. Now, what is the time taken to complete one revolution? That is dt. So we know we have defined that in one revolution per minute, the speed. So that means the synchronous generator will make ns number of revolutions in 1 minute. 1 minute is nothing but 60 seconds. In 60 seconds, if the synchronous generator will make ns number of revolutions, then what is the time taken by one revolution? So therefore, it is given as 60 by ns seconds. Therefore, dt is expressed as 60 by ns seconds. Now, let us substitute these two values in the expression. Therefore, average value of EMF induced per conductor, which is nothing but d phi by dt. So, we know that d phi is equal to phi into p and dt is equal to 60 by ns. So, rearranging the expression, we get p phi ns by 60. We know that ns is equal to 120 f by p. So, substitute this in this expression, we get 2. After cancellation, we get 2 phi f. So, this is the value, this is the average value of EMF induced in a single conductor. Now, actually there will be not one conductor. So, there will be some Z number of conductors. We are deriving the expression for EMF induced per phase. So, per phase there will be Z phase number of conductors. Okay. So, and we also know that Z phase is equal to 2 times of T phase. So, Z phase is equal to 2 times of T phase. Therefore, the final expression for E phase is equal to 4.44 Kp Kd phi f T phase. So, how did we get this expression? The previous expression is average value of EMF induced per conductor is 2 phi f. Okay. So, like that, how many number of conductors are there per phase? There will be Z phase number of conductors. Therefore, EMF induced per phase is given by the expression 2 phi f Z phase. Now, instead of Z phase, we will replace the value of Z phase as 2 times of T phase. So, we have seen here T phase is equal to Z phase by 2. Now, what is Z phase? It is nothing but 2 times of T phase. So, therefore, average value of EMF induced per phase, that is E phase, is equal to 2 phi f into, instead of Z phase, we write it as 2 into T phase. Therefore, E phase can be written as 4 phi f T phase. Now, because the type of winding we have selected is not a concentrated and full pitched winding. So, we have considered, usually for 3-phase alternators, we consider distributed winding and short pitched winding. Therefore, we have to include 2 more factors in your EMF equation. So, what are the 2 factors? That is Kp and Kd. So, Kp is the pitch factor because we have selected a short pitched winding for our 3-phase alternators. Therefore, we have to consider the factor, that is the pitch factor, into the EMF equation. Similarly, as we have considered the distributed winding, so we need to consider the distribution factor or winding factor, that is represented as Kd, into the EMF equation. And also the waveform generated, that is the EMF induced, is of sinusoidal in nature. So because it is of sinusoidal in nature, we need to introduce one more factor, that is form factor, in our EMF equation. So therefore, EMF equation, that is per phase, the EMF induced per phase is represented as 4.44 into Kp Kd phi f T phase volts. Why this 4.44? We know that the form factor for a sinusoidal wave is 1.11, which is a standard value. So if you multiply 4 into 1.11, it is nothing but 4.11. And pitch factor we need to introduce, distribution factor we need to introduce into phi f T phase volts, where phi is the flux per pole, f is the frequency of induced EMF, and T phase is the number of turns per phase. Okay. Therefore, this is the final expression of EMF induced is 4.44 kb Kd phi f T phase volts. Okay. Suppose if the given winding, if the selected winding is of concentrated winding, then the pitch factor will be Kp is equal to 1. If we select a, Kd is equal to 1. If we select a short pitched winding or if we select a full pitched winding, then Kp is equal to 1. Okay. So in short, we can say that for a concentrated winding, Kd is equal to 1, and for a full pitched winding, Kp is equal to 1. For a distributed winding, Kd value is less than 1, and for a short pitched winding, Kp value is less than 1. So this is the EMF equation of an alternator. Now, what will be the value of EMF line voltage induced in a three-phase star connected? Suppose if the three-phase alternator is star connected, then we know that the line voltage is related to the phase voltage as EL is equal to √3 E phase. Suppose if the three-phase alternator is delta connected, then the line voltage and the phase voltage are related as EL is equal to E phase. So this is the EMF. This is the derivation of EMF equation of an alternator. Thank you.